السلام عليكم ورحمة الله وبركاته. طلاب المرحلة الأولى إن شاء الله زينين. محاضرة لهذا اليوم محاضرة السادسة اللي هي ناخذ مزيد من الخصائص والأمثلة حول linear independent and linear dependent. Proposition if S is a finite set of vectors which contains the zero vector, then S is linearly dependent. That means any set S, finite set S, contains zero vector. There is zero vector in this set S, then this set has to be linearly dependent. Proof. Let S is equal to zero vector, has zero vector v2 to vk. This is finite set, and because we say S is finite, and this and observe that 1 0 vector this plus 0 v2 plus until 0 vk, this is equal to 0, because this is 1 0 0 and this is 0, all of them 0, so the result will be 0. Thus C1 0 vector plus C2 v2 plus ck vk equal to 0 doesn't imply does not imply C1 equal to 0, because this is C1 equal 1, not 0. Doesn't imply C1 equal to 0. Hence the set of vectors is not linearly independent. Then thus, by definition, S is linearly dependent. This is finished proof. This is page number 1. Look, I repeat. If a set contains zero vectors, then this set linearly dependent. How can show that? Proof. Let S S contains 0 vectors, and this is finite set, has to be finite set. So this is 0 vector first vector, and this is v2, v3, and so on to vk. This is finite set, contains 0 vector. And observe 1 0 times 0 and 0 times v2 and so on 0 times k. This will be equal to 0. Thus c1 0 vectors plus c2 v2 and so on ck vk equal to 0 doesn't imply c1 equal to 0. Look, c1, this is c1 not equal 0, this is 1 not 0. So hence the set of vectors, sorry, here is not the 0, the set of vectors is not linearly independent, because there is some c's, this is c1 not 0, so this is linearly independent by definition. Thus this is not linearly independent by definition. Thus S is linearly dependent. This is finish the proof. And another proposition let V and W be non-zero vectors. V, W are linearly dependent if and only if, this both sides, if and only if there exists k is not equal to 0, belongs to R, real number, this is k, real number, such that V is equal to KW, If V there is k is not equal to 0 in R, such that V is equal to KW, then these vectors will be linearly dependent. Look, you can prove this proposition. Suppose VW are linearly dependent, both sides are linearly dependent, then there exist constants C1, C2, not all 0. Not all of them, this is C1, both of them 0. Because this is definition of linearly dependent. This is, we assume that VW linearly dependent, so there is C1, C2, not all of them, not both of them 0, such that C1V plus C2W equal to 0. Suppose C1 equal to 0. Then if C1 equals 0, then C2W equal to 0, hence C2 equal to 0 or W equal to 0, because this is equal to 0, so either C2 0 or W 0. But this is contradiction. Since VW are non-zero vectors, because this is both of them non-zero vectors, and at least one of C1 C2 must be non-zero, because C1 C2, because this is VW non-zero, linearly dependent, so must both C1 and C2, not all of them 0, must to be some of one, not one of them, not 0. So if C1 0, we get either C2 0 or W 0, W non-zero. So this is 0, and C1 0 or C2 0. This is contradiction with this assumption that the VW are linearly dependent. So this is therefore C1 is not equal to 0. This is an assumption not correct. We assume C1 equals 0 and we get contradiction. This is contradiction, so this is C1 is not 0. Now if C2 equal to 0, we find a similar contradiction. We find similar contradiction. Hence, C1, C2 are both non-zero. And we calculate V equal to minus C2 over C1, this is times W. So we get K is equal to minus C2 over C1. And this is we see that uh, this is the first direction for this direction we get, and this is implies V is equal to KW. And this is how compute this. Look how compute this. Look here, C1V1 C1V plus C2W, move this here and divide it by C1, you will get this, right? So this is first direction. Second direction prove, I think this is easy. Suppose that V is equal to KW, and with K is not equal to 0, so that means K is not equal to 0, and we can move this here, V minus KW equal to 0, and this is also can make it look like this, plus minus K W equal to 0, and this is linear combination between V and W, and this is first is 1, this is here 1, and here minus K not equal to 0, K, and this is not 0, and this is not 0, so this is linear combination. We get this is linear combination C1, this is look like this is equal C1, this is equal C2, both of them this is not equal to 0, and also this is not equal to 0, so this is both of them not 0, this is not 0, so V and W are linearly dependent. Should be one of them not 0. We can say this is linearly dependent, because linearly independent have to be all of them 0. This is both of them not 0. And this is finish the proof. This is finish the proof of our proposition. Now we take more example. About this to understand. Look, we take this example. This is example 1. Determine if V1, V2, V3 given below are linearly independent or dependent. Or or dependent. V1 is equal to 1 1 1. V2 is equal to 2 1 0. V3 is equal to 3 2 1. We try to find solution. We try to find a RF. Try to find, solve this is by Gauss elimination, Gauss-Jordan elimination. Look like this, C1 V1 plus C2 V2 plus C3 V3 is equal to 0. This is belongs to R3 times 1. So here C1 with V1 1 1, this is V1, and plus C2 with V2 2 1 0 plus C3 with V3 3 2 1. This is will be equal to 0 0 0. And now we can move and sum, get the same at the same time, move and sum. And here C1, here's C1, here's C1, and here plus 2C2, and here plus 3C3, and here C1 plus C2 plus 2C3. This is also equal to 0, this is also equal to 0, and this is C1 plus C2 0, and this is C3 plus C3 equal to 0. Now we try to do it by Gauss-Jordan elimination. This is page number 2, and this is page now number 3. We move this is to matrix, look like this. Now move this is to matrix, we get 1 2 3 0, and here 1 1 2 0, and here 1 0 1 0, because here there is no C2, so this is 0, and here 1 C1 2 C2 2 3 C3 3, and here 0, and here's 1 C1 1 C2 2 C3, and here 1 C1 0 C2 1 C3, and this is equal to 0. So now try to do this system by Gauss-Jordan elimination. Look how can do it. R1 minus R2 right in R2, also R1 minus R3 right in R3. How we get this is the same 1 2 3 0, and this is will be 1 minus 1 equals 0, 2 minus 1 equal 1, 3 minus 2 equal to 1, 0 minus 0 will be 0, and here 1 minus 1 will be 0, 2 minus 0 2, also 3 minus 2 3 minus 1 will be 2, and here 0 minus 0 equal to 0. And now try to make this is 0. This is 1, this is 1, also this is we can write 2 R2 minus R3, right, in R3. This is implies this is the same 1 2 3 0, and here the same also 0 1 1 0, and here we can subtract 0 minus 0 will be 0 1. This is 2 minus 2 0, and here also 2 minus 2 0, and here 0 minus 0 will be 0. Look, this is all of them 0, so this is a problem. Now we try to make this 0. Try to make this 0 will be 2 R2 minus R1, right, in R1. So this is implies will be right in R1 0 sorry, minus 2 plus R1, minus 2 plus R1 to get this is 1. This is minus 2 0 plus 1 will be 1, and this is minus 2 plus 2 will be 0, minus 2 plus 3 will be 1, and here 0 0 will be 0, and this is the same 0 1 1 0, and this is the same. Now I can't do this 0. If I do this 0, this is will be changed. So this is final. This is arif of this system. Now we can look about this. How we get from this? We get from this C1 plus C3 equal to 0, right? And here, from here, we get C2 plus C3 also equal to 0. So from this one we get C1 equal to minus C3 and from this C2 equal also minus C3. Both of them, C1 and C2, depends on C3. So this is C3 is free. This is for any value of C3, C1 depend on C3 and C2 depend on C3, and this is maybe not equal to 0, because if C3 equal to 1, this implies C1 equal to minus 1, and also implies and C2 also equal to minus 1. So this is not all of them 0. If we take also, of course, if we take C3 0, will be this 0 and all of them 0, but this not just one solution, not unique solution. This is there are infinitely many solutions. There are infinitely many solutions. Look, we can move. We can take this table. This is C1. This is C2. This is C3. And here, if here 0, of course this is 0. Also this is 0. But if here equal 1, So this is minus 1 and this is also minus 1. If we take here 2, so this is minus 2 also, this is minus 2. If we take here minus 0 will be, this is will be 1, this is also will be 1. Look, C1 and C2 depends on value of C3, so there are infinitely many solutions, not unique solution 0 0 0. So now we can see this mean minus C3 V1 minus C3 V2 plus C3 V3, this will be equal to 0. This is will be equal to 0. For any value of C3, for any value of C3, and if we take C3 equal to 1, take C3 equal to 1, this is will be implies minus V1 minus V2 plus V3 equal to 0, and this is implies V3 equal to V1 plus V2. So that means V3 depends on V1 and V3. Sum V1 plus V2 plus V1 implies V3. Come back to the original example. Here this is V1, V2, V3. So look, I get this is V1 plus V2 equal to V3. If I sum V1 plus V2 will be equal to V3. 1 plus 2 equal to 3, and 1 plus 1 equal to 1 plus 0 equal to 1. So V3 equal to V1 plus V2. V1 plus V2. Right? I think this is clear. Now we look another example. Look at another example. Take this is another example. Now 4, this is page 4. Look for about another example. Example 2. Determine if V1, V2, V3 given below are linearly independent or dependent. V1 is equal to 1003. V2 is equal to 3120, and V3 is equal to 212 minus 3. Solution. Now we also do the same. C1 V1 plus C2 V2 plus C3 V3 equal to 0. This belongs to R 4 times 1, because there are 4 rows. Now substitute here. This is C1 V1 1003 plus C2 V2 3120 plus C3 212 minus 3. This will be equal to 0 0 0 0. This is 4 by 1 times 1. Now move and sum at the same time. This is C1 plus 3C2, and this is plus 2C3, and this is C1 0 and C2 1, C2 here, C2, and plus C3, just this, and here also 0, here 2C2 plus 2C3 here, and the last one will be 3C1 plus this is 0 minus 3C3. This will be equal to 0 0 0 0. And now we get this. We can move it to matrix. And solve by Gauss-Jordan elimination. Move to matrix. 1, this is 1, and this is a 3, and this is 2, this is 0 here, and here 0 because C1 0, and C2 1, and C3 also 1, and here 0, and here 0 also, here 2, here 2, here 0, and here 3 0 minus 3 0. Try to find RDIF for this system. Try to make this 0. Now 3 R1 minus R4 minus right in R4, this is implies 1 3 2, and here 0, and here 0 1 1 0, and here 0 2 2 0, and here will be 3 minus 3 will be 0. The 6 9 here will be 9 minus 0 9, and here 6 plus 3 will be 9, and here will be 0. And now try to make this 0 and this 0. We get 2 R2 minus R3 right in R3. Also 9 R2 minus R4 right in R4 implies this will be implies right in R3 and 4, so this is the same 1 3 2, this is here 0, and here the same 0 1 1 0, and here we can do it. 2 minus 2 will be 0. Here 0, of course. Here 2 minus 2 0. Also here 2 minus 2 0, and here 0. This is all of them 0. And here 9 0 0, and the 9 minus 9 will be 0. Also here 9 minus 9 0. Also this is cancel row, and this is cancel row, all of them 0. Now try to make this is 0. Will be get minus 3 R2 plus R1 right in R1. This is implies right in R1. So this is 0 plus 1 will be 1, and here minus 3 plus 3 will be 0, and here minus 3 plus 1 will be minus 1, and here 0, and here is the same 0 1 1 0, and this is all of them 0. This is page number 5. And now this is arif. We can move more than this. So this is arif. What we get from this, we get that C1 minus, from this we get that C1 minus C3 equal to 0. Also C2 plus C3 equal to 0. So from this one we get C1 equal to C3. From this we get C2 is equal to minus C3. So C1 C2 depend on C3. This means that if we write linear combination of these vectors, if from this one, from this equation, or this, of course, from this equation, we can substitute by C1 by C3 and C2 minus C3, because C1 equal to C3, also C2 equal to minus C3. So this will be implies that C3 V1 plus, sorry, minus here, because this is minus C3 V2 plus C3 equal C3 V3 equal to 0. We get this for any value of C3. This is true for any value of C3. Take any value. We can take C3 equal to 1. Take C3 equal to 1. So we get, if we take here, we get V1 minus V2 plus V3 equal to 0. So this implies that V3 is equal to V2 minus V1. So V3 depends on V2 and V1. We can come back to this example. We say that V3 is equal to V2 minus V1. So if we subtract 3 minus 1 will be 2, or 1 minus 0, 0, 2 minus 0, 0, 0 minus 3 will be minus 3. So that means V1, V2, V3 are linearly dependent. This is by proposition. I think this is enough for today. So thank you very much.